Okay. Hi. So, welcome to this class. It's the first class of 2021, and while we wait for more people to come in, let's do the fun problem of the day. All right, so I'll start going over the fun problem of the day now. So, the problem is from the year 2004, and in 2004, February 29th fell on a Sunday. And so you want to find the next year that February 29th falls on a Sunday. So first of all, we can see that we know that February 29th only happens on leap years. And so during the 4-year gap between each leap year, okay, sorry. And so during the 4-year gap between leap years, between a normal year, each day shifts by 1, but after a leap year, there's a shift of 2. And so after 3 normal years and then a leap year, there's a total of 2 plus 1 plus 1 plus 1 equals 5 days. And so there's a shift of 5 days between each leap year. And so this isn't a multiple of 7. So in order for the next February 29th to fall on a Sunday, you need to wait 7 more leap years. And that causes a shift of 35 days, which is equivalent to a few weeks worth of time with no days left over. And so to wait 7 more leap years, the seventh leap year from 2004 is 2004 plus 4 times 7 because there's 4 years between each leap year. and this is 2032. So the answer is 2032. Are there any questions? All right. So now I'll be moving on to this week's topic, which is number theory. And so we're going to cover factoring techniques, modular arithmetic, and integer polynomials. And so here's an example problem for factoring techniques. All right, so I'll start going over this now. So the problem wants you to find the value of the square root of 40 to the fourth minus 30 to the fourth. So first of all, you can see that this is clearly a difference of squares. And so this equals square root of 40 squared minus 30 squared times 40 squared plus 30 squared. And by the Pythagorean theorem, or whatever you want, you can see that 40 squared plus 30 squared is 50 squared. You can also verify this manually, but you can just remember it's a 3, 4, 5 Pythagorean triple. And so this is equal to square root of 50 squared times 40 squared minus 30 squared. And this is equal to 50 times the square root of 40 minus 30 times 40 plus 30. And this factorization under the square root follows from another application of different squares here. And so this is equivalent to 50 times the square root of 10 times 70. And this is simply equal to 500 root 7. So does anyone have any questions? All right. If not, let's move on to the next question. Okay, I'm going to start going over this problem now. So the problem wants to find the sum of all the distinct prime factors of 25 cubed minus 27 cubed. Actually, yeah, okay. So you can factor this as 25 equals 5 squared and 27 equals 3 cubed. So you can simplify this down to 5 to the 6th minus 3 to the 6th. And by difference of squares, you have that this is equal to 5 cubed minus 3 cubed times 5 cubed plus 3 cubed. And so this is also a sum and difference of cubes. And so you can apply the difference of cubes to get on 5 cubed minus 3 cubed to get 5 minus 3 times 5 squared plus 5 times 3 plus 3 squared. And you can apply the sum of cubes to 5 cubed plus 3 cubed to get 5 plus 3 times 5 squared. minus 5 times 3 plus 3 squared. And so this is equal to 2 times 49 times 8 times 19. Want to simplify all of this down. And so this equals 2 to the fourth times 7 squared times 19. And so you want the sum of all the distinct prime factors. And so the distinct prime factors are 2, 7, and 19. And when you add these up, the sum is 28. So, sorry. So does anyone have any questions? All right. If not, I'm going to move on to modular arithmetic. So, a residue. You say that A is the mod M residue of N if this is true, and this is notation that means N is congruent, N is red, N is congruent to A mod M. And in general, the most common form of this is for A is less than or equal to A, 0 is less than or equal to A is less than M. And so in general, two integers A and B are congruent mod N if and only if A minus B is a multiple of N. And so you can also word it this way. A is congruent to B mod M if A minus B over N is an integer. And if not, then this is notation for A is not congruent to B mod N, and it just means that they don't have the same remainder when you divide them by N. And some useful facts to know about modular arithmetic, and these are very similar to just the rules for equations. A plus if A is congruent to B mod M. Sorry. So if A is congruent to B mod M and C is congruent to D mod M, then you have that A plus C is congruent to B plus D mod M. And you also have that A minus C is congruent to B minus D mod M. And A times C equals B times D mod M. But division is where it doesn't match with the normal rules of equations. So in division in modular arithmetic, it's not always reversible. So you can't just multiply by something and divide by the same thing. And you can't always say that it's necessarily true. Okay, so A divided by E is congruent to B divided by E mod M divided by GCD of M and E. And if M and E are relatively prime, then you can just treat it like you would in addition, subtraction, or multiplication. And if not, then you need to divide by their GCD. And for exponents, it also works just like a normal equation. All right, so here's an example for modular arithmetic. So find the units digit of the sum. All right, so I'll just start going over this because it's really easy. So to find the units digit of this sum, you can ignore everything in here except the units digits. And logically, this makes sense. And one way to show this is just by taking all of these modulo 10. Because the units digit is the sum modulo 10. And so 52343 plus 3452341 plus 998,768 plus 5678549 mod 10 is congruent to, so this is congruent to 3, and this is congruent to 1, and this is congruent to 8, and this is congruent to 9. So with 3 plus 1 plus 8 plus 9 mod 10, and this is congruent to 1, and that means that the units digit of this sum is 1. Are there any questions? All right. So here's another problem. And by the way, um, this thing up here should say AMC12, not MAC. That's a typo. All right, I'll start going over this now. So we let k be 2008 squared plus 2 to the 2008. And so you want to find the unit digit of k squared plus 2 to the k. And so we can split this into finding the unit digit of k squared and the unit digit of 2 to the k. And first we can do the k squared. So k mod 10 is congruent to 2008 squared plus 2 to the 2008. And that's because that's what 10 is equal to. And this is 8 squared. And so as for 2, you can list out the powers of 2. So mod 10, so it's 2, 4, 8, 6, 2, 4, 8, 6, and so on. So it repeats every 4 digits. And so to do the 2008 is in the 4th digit of a cycle. So it's 8 squared plus 6, and this equals 70, which is congruent to 0 mod 10. And so the unit digit of k squared is 0. And now we can easily see that 4 divides k because 4 divides 2008 squared and 4 divides 2 to the 2008. So then 2 to the k is just congruent to 6 mod 10. So the unit digit of 2 to the k is 6. And when you add these up, you get that the unit digit of k squared plus 2 to the k is 6. Alright, so are there any questions? All right. If not, let's move on to another example. All right. So I'll start explaining this problem now. So you want to find the remainder when 2 to the 2001 is divided by 2 to the 7th minus 1. And so one important thing to notice here is that 2 to the 7th is congruent to 1 mod 2 to the 7th minus 1. And so we can split 2 to the 2001 into 2 to the 6th times 2 to the 7th to the 285. The exact number here doesn't matter, but it turned out to be 285. The exact number here doesn't matter. You just really need that 2001 is congruent to 6 mod 7. And so it equals 2 to the 6th times 2 to the 7th to the sum power. And so this is congruent to 2 to the 6th times 1 to the 285 or whatever mod 2 to the 7th minus 1. And so this is just goes away and you're left with 2 to the 6th, which is equal to 64 mod 2 to the 7th minus 1. And so are there any questions? All right. If not, I'll move on to the Chinese remainder theorem. So let m and n be relatively prime numbers. And then there is a unique solution for each possible combination of moduluses m and n for each modulus mn. Basically, if you have that x is congruent to a mod m and x is congruent to b mod n, where GCD of m and n equals 1, where GCD of m and n equals 1, then you're guaranteed that x has a solution mod m n, m times n. That's basically what it's saying. So here's an example of the Chinese remainder theorem. And it's pretty, and this is a pretty small case, so Alright, I'll start going over this problem now. So, Chinese remainder theorem guarantees us that there is a solution for this modulo m times n. And so first of all, we should find what this m times n is. And so m times n equals 3 times 4, and that's equal to 12. And so you want to find the integers satisfying 2 mod 3 and 3 mod 4. And so you can just list out the integers less than 12 that are 3 mod 4 and see which one of them satisfies 2 mod 3. So in increasing order, the integers that are 3 mod 4 are 3, 7, and 11. And this is 0 mod 3, this is 1 mod 3, and 11 is 2 mod 3. So the general formula for integers satisfying 2 mod 3 and 3 mod 4 is 11 mod 12. And an even faster way to do this is notice that this is negative 1 mod 3, and this is negative 1 mod 4. So combined, it's negative 1 mod 12, and that's congruent to 11. So are there any questions? All right. If not, let's move on to another problem. So someone wanted to see the Chinese remainder slide again. So here it is. So just a little hint for, sorry, this problem, a little hint would be that you're effectively trying to find this thing mod 100, and you can find them by combining mod 4 and mod 25 and using CRT. Alright, so I'll start going over this. So first of all, you can see that 1032. Okay, so you want to find the last two digits of 1032 to the 1032. So first of all, you can see that 1032 to the power of 1032 is congruent to 32 mod 1032 mod 100. And this just makes the denominator easier. And by using and then so by using CRT, you know that finding this 32 to the 1032 mod 4 and mod 25 is sufficient to find it mod 100. So clearly 32 to the 1032 is 0 mod 4. And you can also do some calculations for 7 to the 1032, and that's because 32 to the 1032 is congruent to 7 to the power of 1032 mod 25. And once you calculate it, you can see that this is congruent to 1 mod 25. So you can list out the 1 mod 25, the numbers that are 1 mod 25 that are less than 100, and in increasing order, they are 1, 26, 51, and 76. And the only one that's divisible by 4 is 76. So the answer is 76 mod 100. And so the last two digits of 1032 to the 1032 is 76. Are there any questions? All right. If not, I'll be moving on to Fermat's Little theorem, which is often abbreviated as FLT. And so let P be a prime number and let A be a positive integer that is not divisible by P. Then Fermat's Little theorem states that A to the power of P minus 1 is congruent to 1 mod P. And the reason it says A is not divisible by P is because otherwise this would be 0 for clear reasons. So here's an example. And the latex didn't render here. This should instead be 3 to the 2002, not 332,002. Alright, so I'll start going over this problem now. So applying Fermat's Little theorem, or FLT, you know that 3 to the 11 minus 1 is congruent to 1 mod 11. And so when you simplify this, you get 3 to the 10 is congruent to 1 mod 11. And so since you just want to find 3 to the 2002 mod 11, you have that 3 to the 2002 is 3 squared times 3 to the 2000, which is 3 squared times 3 to the 10 to the power of 200, which is 3 squared times 1 to the 200 mod 11, and this is just equal to 9. So are there any questions? Alright, if not, let's move on to the remainder theorem. So the remainder theorem basically says that when you divide a polynomial, so the main point of the remainder theorem is here. And it's basically when you divide a polynomial f of x by the linear term x minus c, the resulting remainder is f of c. Alright, so this is an example of how you would use the remainder theorem. So you want to find the remainder of 2 to the x squared minus 5x minus 1 after it's divided by x minus 3. And so by applying the remainder theorem, the answer is just f of 3. And when you plug in x equals 3 here, you get this, and when you simplify it down, it's just 2. And you don't need to use long division this way. And this is a Euclidean algorithm for polynomials. So this is basically what it says. Alright. It works basically in the same way as the Euclidean algorithm for integers. And you can also multiply by like terms like x squared plus x plus 1. You're not limited to just integers when you're doing Euclidean algorithm for polynomials. Alright, on that note, please try to apply the Euclidean algorithm in here. Alright, so I'll start going over this problem now. So compute the GCD of x to the fifth minus x squared minus x minus 1 and x to the fourth plus x cubed minus x squared minus 2x minus 1. So here I'll just write AB as to denote GCD of A and B. Alright, so you want to find their GCD. So x to the fifth minus x squared minus x minus 1 and x to the fourth plus x cubed minus x squared minus 2x minus 1. And so this is x to the fifth, and you can start applying the Euclidean algorithm. And so you can subtract x times this thing, x to the fourth plus x cubed minus x squared minus 2x minus 1, and x to the fourth plus, yeah. And so when you expand this out and simplify it, you just get negative x to the fourth plus x cubed plus x squared minus 1 and x to the fourth plus x cubed minus x squared minus 2x minus 1. Alright, and now you can add this to the left side. So it's equal to negative x to the fourth plus x cubed plus x squared minus 1 plus x to the fourth plus x cubed minus x squared minus 2x minus 1 and x to the fourth plus x cubed minus x squared minus 2x minus 1. And when you do the addition, you just get that it's equal to 2x cubed minus 2x minus 2 and x to the fourth plus x cubed minus x squared minus 2x minus 1. And now you can take out a factor of 2 from the left side because you know that 2 won't be a factor of the GCD. And that's because when you put in x equals 0 to here, you get negative 1. And that means that 2 doesn't divide this because 0 is an integer. So this is equal to x cubed minus x minus 1 and x to the fourth plus x cubed minus x squared minus 2x minus 1. And now you can subtract out x times this from the right side. Right. So that equals x cubed minus x minus 1 and x to the fourth plus x cubed minus x squared minus 2x minus 1 minus x times x cubed minus x minus 1. And you can simplify this to x cubed minus x minus 1 and x cubed minus x minus 1. And so these two are equal to each other. So it's just the answer is x cubed minus x minus 1. So are there any questions? All right. So the rational root theorem. So when you're given a polynomial, n of x equals a, a of n times x to the n plus, yeah, this way. This is a pretty standard way of writing an nth degree polynomial. And so with integer coefficients, and a of n is not equal to 0. And the rational root theorem states that if n of x has rational roots in this form with p and q relatively prime, with p and q relatively prime, then p divides a0 and q divides an. And every rational root of a polynomial where a of 1 equals 1 that has integer coefficients must be an integer. Alright, so here's an example of a use for the rational root theorem. And now there's basically no time left, so I'll just directly go over it. So by the rational root theorem, the numerator of any rational root divides 8, and the denominator of any rational root divides 1. And so this tells you that any rational root is an integer. So we can just try rational roots here. You can try -8, -4, -2, -1, 1, 2, 4, 8. And you can try any of these that you want until you find one. And once you find any of them, you can just x use the you can just use polynomial division, and x to the x cubed minus 5x squared plus 2x plus 8 divided by x minus c, where c is whatever value you found in here. And after you find what this is, you can use the quadratic formula to find the roots. And in the end, it turns out that this thing factors as x minus 4 times x minus 2 times x plus 1. All right. And that's it for today's class. Thank you for coming. And homework and handouts will be posted later. And yeah, bye.